Hello guys, so welcome back to another lab in our course. This is lab 6, half-wave rectifiers. In this lab, we're gonna discuss or study the two half-wave rectifiers that we studied in the lectures, the positive half-wave rectifier and the negative half-wave rectifier. And also we're gonna study the effect of the breakdown voltage on the output DC. Basically, in these circuits, we measure the efficiency of these circuits by measuring the output DC or the output average value. The higher this value is, the higher or the higher the efficiency or the better the rectifier is. And of course, if you have a diode with small breakdown voltage, this DC will the diode may break down and this DC voltage will decrease. Okay, so let's guys start with the positive half-wave rectifier. This guy in here. Okay, we're gonna construct this circuit. I already did this for you here. And this probe here will measure our DC output, the DC of the voltage DC of the resistor or the load, which would be, for example, your charger or something. So let's start this. Okay. So the first step is to measure the input. So here is the input. So as you see, guys, the input is Euro standard input. The maximum should be around 155. So let's go to Y max. So it's 154 or 155 basically, very close to 155. And the minimum, if we go to the minimum, again, minus 155. Very close to each other, the model of this, this practical source usually have some deficiency. So you will not see the positive and the negative exactly the same. But that's fine. This is just, a model for our practical outlet, which has 10 RMS, which is around 155 with 60 hertz, frequency. Okay, this is the input. Let's now explore VD and VO or VD and VR. Okay. So let's now measure VA and VB, which is basically VD and VR or VLoad. Okay. So we're gonna start by VD, which is the channel A here. So here is, let's do this setting. So YT, this should be DC, and this should be 0 with channel B. And reverse. Okay, everything is the same, except here. So let's do that as 2. Okay, and why at 2? Because if we keep it at 100, so this part here, this 100, this part, which is basically the clipping part of the positive, half wave, half of the sine wave, is basically very small to see. And we studied in the lecture that there is a clipping here at 0.7, and we said that this 0.7 is very, very small compared to the minimum value here, which is minus 155, so that you will not notice this 0.7. So to make it clear, we're gonna decrease the voltage per division to 2, just 2. And now it's clear. Now this is the 0.7 that I'm telling you about. So let's measure it. So let's make it select a trace, go to Y max. Yeah. So basically here it's around 800 millivolt, which is basically 0.7, very close to 0.7, our theoretical value. So in the lecture, we draw or we sketch or we plot VD, and there was a clipping in the positive half cycle at 0.7. Okay, this is very close to it. Now let's measure the the minimum voltage. So let's bring this back to 100, as I see here in the report or the manual. So we're gonna go to 100. Good. Now let's go to the min. And look, guys, the min is minus 155.3. Okay. So that's why we cannot see or notice, this 0.7 clipping, because it's very, very small to minus 155. And that's the reason that I told you about, that the ideal diode model, works perfectly with such applications. So you can use the ideal diode model, although we didn't use it, but just because in the lecture we wanted to cover the difficult, the more difficult, situations. which is constant voltage model, of course. But if we use the ideal model, it should give you very accurate results. Okay, because the zero point 0.7 clipping is really, really very small to the minimum voltage. As you see here, it's not noticeable at all. Okay, we cannot notice it, or we cannot, observe it at all. So this is all for the VA or VD. So let's now, guys, measure VB, or the load voltage, or the resistor voltage. So we're gonna set the the oscilloscope to these settings here. We're gonna make first A as 0, then set this to DC, so we can measure VB without measuring or without showing the voltage on A. Then we're gonna move this marker to the max. Looks like this is the max, but let's check more. Oh, it's not set to B. So select a trace. It's B, okay. Now we go to the max. Okay. So the max here is 154.5, which is really not exactly 155, the 155 that we were expecting. And this is because the maximum here, because there is a clipping, a very small clipping on the diode, which is 0.7, around 0.7. That's why you cannot see the maximum voltage here exactly as the input. Okay, and this max here is basically very comparable to this value here, which is the maximum of the input minus the 0.7 drop on the diode that we measured, and it was around 800 millivolt, which is very close to 0.7. Okay, so that's basically the maximum of VB. And now it's time to measure the DC. So we're gonna close this, and the DC is really very easy. So since we put a probe here, the probe will just measure the DC for us. So VDC, which is the average value of the load voltage, is 49.1. And we know the theoretical value for this. In the lecture, the theoretical value was Vmax over pi if we use the ideal voltage model. But if we use the practical model, or the constant voltage model, so this value will be Vmax minus 0.7. I didn't cover this in the lecture because it was a little bit of complication. So I opted to just make it very simple to you using the ideal model. But you can basically use the constant voltage model to estimate theoretically the average value, and it will be Vmax minus 0.7 over pi, which is basically Vmax minus 0.7. Okay, this will will be calculated to 49.2 or 0.3, which is really very close to what we have here, 49.1. Okay. Finally, Kirchhoff always work as usual. So we're gonna compare if we add VD and VA together, and we should get the input. This is basically a very basic step for you guys to check that you are in the correct way. Okay, so we're gonna choose here add, and pause DC here. There is some delay as usual, so we're gonna make none here, then single, and here it is. This is the addition. Okay, and we can go, for example, to any of the max here. So it's 155.341, and we can go to set this to the min. It is minus, that's exactly the same. Okay, and this is basically the input. If you measure the input back here, you will find this is exactly the input. Okay, so let's go to the max, and this sets this to the min. Exactly the input. Okay, guys, that was experiment 1. Then very important here to stop running the simulation before going to experiment 2. And that's because in experiment 2, we're gonna change the properties of the diode to make its breakdown voltage, very small, so that we can, measure the effect of the breakdown voltage on the output DC here. Okay, guys, thank you very much for watching this video, and stay tuned for the next video. Thank you very much. Bye-bye.